So imagine you were to take a brand new golf ball, right?
Yeah.
And you take it into a workshop, and you just sand off all the dimples,
Okay, sanding them completely off.
completely off. You polish it until it is perfectly, insanely smooth,
Mhm.
like a glossy, frictionless sports car kind of finish.
Right, a perfect sphere.
Yeah, exactly.
Yeah.
And then you hand that perfect sphere to Tiger Woods on the first tee. Something incredibly bizarre would happen.
It really would.
He would, swing with all his might. The club would connect perfectly, and that sleek, incredibly aerodynamic-looking ball it would fall out of the sky like a
Like
stone.
an absolute rock.
I mean, it wouldn't even travel half the distance of a standard, cheap, bumpy golf ball you'd buy at the store.
It is a stunning visual to imagine, for sure, but it's entirely accurate. That smooth, perfect sphere would just be an absolute aerodynamic disaster.
And that is exactly why we are here. Welcome to another deep dive. Today, we are tackling a subject that, honestly, it completely breaks our everyday intuition.
It really throws a wrench in how we think the physical world works.
It does, because, if you think about it, for you, the listener, humanity spends literally billions of dollars trying to make things move fast by making them smooth.
Oh, absolutely.
We wax our cars, we polish the aluminum wings on fighter jets, we design high-speed trains to look like these sleek, frictionless bullets.
Right. The whole prevailing logic of our world seems to be that smooth objects slip through the air easily, and rough objects, well, they get held back.
Exactly, and that makes perfect sense,
Yeah.
based on how we interact with the solid world every single day.
Yeah, I mean, if you slide a wooden block across rough sandpaper, it stops immediately.
Like the friction just grabs it.
But if you slide that same block across smooth ice, it just glides forever.
Right.
We are completely hardwired to associate smooth surfaces with speed and efficiency.
But the golf ball just throws that entire paradigm right out the window.
It flips it completely upside down.
So today, our mission for this deep dive is to decode the invisible physics of fluids. We are trying to understand why, under very specific conditions, manufacturing chaos and roughness on the surface of an object actually makes it slice through the air infinitely better than perfect smoothness.
It is a fascinating paradox.
And we are pulling from some seriously dense, heavy heating sources today to figure this out. We've got the Foundational Fluid Dynamics textbooks by John D. Anderson and Frank M. White.
Both absolute classics in the engineering world.
Yeah, and we are pairing those with some highly advanced computational fluid dynamics manuals, or CFD manuals, directly from ENSYS Fluent.
So we are going to take all of that really complex, dense mathematics and use it to dissect the sheer genius of that tiny dimpled sphere.
Right. But to understand why the golf ball is engineered the exact way it is, we first have to understand the invisible, microscopic war that is just constantly being waged against it the second it leaves the tee.
Exactly. We have to start at the absolute foundation. And that means defining what we actually mean when we use the word fluid.
Let's start right there. Because, honestly, if you stop me on the street and ask me what a fluid is, I'm pointing to a glass of water.
Of course. Most people would.
I am definitely not pointing to the empty air around us. But from a physics standpoint, air is a fluid, isn't it?
It absolutely is. And Frank M. White's textbook lays this distinction out so brilliantly. In the realm of mechanics, all matter in the universe is basically divided into only two states. You have fluids and you have solids.
Just two. Okay.
Right. And the technical distinction between them has absolutely nothing to do with whether they are wet or dry.
Okay, so what is the distinction then?
It has entirely to do with how they react to something called a shear stress.
A shear stress. Okay, I'm getting a physical visualization for that because that sounds like engineering jargon.
Fair enough. Imagine you place your hand flat on top of a really thick, heavy textbook lying on a table.
Okay, I've got my hand on the book.
Now press down slightly and try to slide your hand forward, right? Parallel to the cover of the book.
Okay, pushing sideways across the cover.
Exactly. That tangential force, that sliding, rubbing force acting parallel to the surface, that is a shear stress.
Okay, I can clearly picture that. My hand is applying a sideways, dragging force across the top of the book.
Now think about how the solid book reacts to that.
Well, it just kind of sits there.
Right. It might flex a microscopic amount. It might, bend a tiny little bit under the friction of your hand, but eventually it holds its ground.
It fights back and stays put.
Yes. A solid can resist a shear stress by what we call a static deformation. It takes the sliding force, bends a tiny bit, and then pushes back, establishing an equilibrium.
So a solid says, no, you can't slide me anymore.
Exactly. But a fluid cannot do that.
It can't fight back.
No, A fluid is defined literally by its absolute inability to resist a shear stress.
Inability.
Total inability.
Wow.
Any shear stress applied to a fluid, no matter how infinitesimally small the force is, will result in motion. The fluid will just move and deform continuously for as long as that sliding force is applied to it. It never, ever establishes a static equilibrium against a shear stress.
So it just perpetually yields to it. You push it sideways and it just flows out of the way.
It just flows. Isaac Newton actually formalized this all the way back in 1687 in his Principia.
Oh, wow. So this goes way back.
Yeah. He defined a fluid as anybody whose parts yield to any force impressed on it, and by yielding are easily moved among themselves.
That's a great definition.
Because both water and air are really just aggregations of molecules moving about freely relative to each other, they both yield to shear stress. And therefore, mathematically and physically, they are both fluids.
So translating that to our golf ball, the moment a golf ball is flying through the air at, 150 miles an hour, it is essentially trying to force its way through this dense ocean of molecules that are constantly yielding and flowing around it.
They are yielding, yes, but that ocean also pushes back.
And it pushes back hard, I'm assuming.
Extremely hard. And this actually brings us to a really fascinating mathematical corollary that White brings up in his text, specifically regarding fluids at rest.
Okay. What happens when they are at rest?
Well, think about it. If a fluid continuously deforms under any shear stress, like we just established, then logically, a fluid that is completely at rest, not moving at all, must be experiencing exactly zero shear stress.
Okay, yeah, that totally tracks. Because if it had even a tiny bit of shear stress, it would be flowing.
Exactly. In structural analysis, this state of rest is called the hydrostatic stress condition.
Hydrostatic stress condition. Got it.
And White points out that in this specific condition, a mathematical tool called Moore's circle for stress reduces down to a single point.
Okay, pause right there. You just threw Moore's circle and hydrostatic stress condition at me in the same breath.
I did. Sorry about that.
I am definitely going to need you to translate that into English for anyone who didn't spend 4 years trapped in an engineering library. What exactly is Moore's circle?
That is a very fair point. So Moore's circle is basically a graphical way that engineers figure out what kinds of forces are acting on a material from all different angles.
Okay, a graph of forces.
Right. Imagine you cut a tiny microscopic cube out of a material. You have forces pushing straight in on the flat sides of the cube. Those are called normal stresses. Think of that like pressure.
Normal stress equals pressure pushing straight in.
Yes. And then you have forces trying to slide along the faces of the cube. Those are our shear stresses we just talked about.
The rubbing forces.
Exactly. So Moore's circle simply plots those normal forces against the sliding forces on a two-dimensional graph.
Okay, I'm picturing an X and Y axis.
Right. For a solid piece of metal that's under a heavy load, you might have lots of normal stress pushing in and lots of shear stress trying to rip it apart sideways at the same time.
So the graph would be pretty complicated.
It would. When you plot all those stresses from every angle, you get this big, wide circle on the graph showing all these complex combinations of forces.
But earlier you said for a fluid at rest.
Right. For a fluid perfectly at rest, there is absolutely zero shear stress on any plane cut at any angle through that fluid.
Because it's not moving.
Exactly. The only force acting on it is the normal stress, the static pressure pushing in equally from all sides.
So what happens to the graph?
Well, if you go to plot that on the Moore's circle graph, there is simply no shear value to give the circle any height or width. So the entire complex circle collapses completely down into a single solitary point on the horizontal axis.
Oh, wow. That is actually a really beautiful way to visualize it.
Isn't it?
The math literally shrinks to a single dot because the fluid is just sitting there in this perfect pressurized equilibrium, just waiting to be disturbed.
And a 150-mile-per-hour golf ball is a massive, violent disturbance.
I can imagine.
When the ball smashes through that resting fluid, the fluid exerts resistance, and we call that resistance drag.
Drag. The enemy of speed.
The ultimate enemy. But our sources are very, very careful to specify that drag is not just one big monolithic force.
It's not.
No. It is incredibly important for aerodynamics to separate it into two distinct categories: friction drag and pressure drag.
Friction and pressure. Okay, let's break those down because I know this distinction is the foundation of the whole dimple paradox we're trying to solve today.
It really is. So friction drag is exactly what we were just talking about with shear stress. It is the integrated shear stress sliding along the surface of the object.
So just the physical scraping of the air.
Right. As the fluid molecules rush past the object, they physically rub against the skin. Friction drag is that literal physical scraping of the fluid against the surface area.
I picture that like rug burn. If you slide across a carpet, that heat and that resistance you feel, that's friction drag.
That is a perfect physical analog. It's fluid rug burn.
Got it. And what about the other one? Pressure drag.
Now, pressure drag, which is also sometimes referred to in literature as form drag, is entirely different.
Form drag, meaning it's based on the form or shape.
Exactly. Pressure drag has to do with the macro shape of the object. When something moves rapidly through a fluid, it rams into the fluid at the very front, creating a massive zone of high pressure.
Because it's compressing the air in front of it.
Right. And simultaneously, it leaves this chaotic, churning wake of low pressure right behind it.
So it's basically punching a hole in the air, it's creating high pressure on its face, and leaving this empty, low-pressure void on its back.
Yes. And because physics absolutely abhors an imbalance, the high pressure on the front is constantly pushing backward, and the low-pressure void on the back is literally sucking the object backward.
Wow.
That massive pressure differential from front to back, that is pressure drag.
Okay, let me make sure I have this straight. So
Yeah.
friction drag is the air rubbing the sides, and pressure drag is the air pushing the front and sucking the back.
You've got it perfectly. And here is where the shape of the object dictates the entire game of aerodynamics.
How?
Well, John D. Anderson's textbook provides these two extreme geometric examples to illustrate how these forces balance out. He compares a flat plate and a circular cylinder.
Okay, let's visualize the flat plate first.
Imagine a very thin, perfectly flat metal plate. You're holding it horizontally, perfectly aligned with the flowing wind.
Like slicing it through the air sideways.
Exactly. The air hits the incredibly thin front edge and just glides smoothly along the huge top and bottom surfaces.
Right.
Because the plate is so incredibly thin, it doesn't really punch a big hole in the air. It doesn't leave a wake behind it.
So there's no void sucking it backward.
None. Therefore, for a flat plate parallel to the flow, virtually 100% of the drag it experiences is friction drag. There is almost zero pressure drag.
That makes total sense. I mean, it has tons of surface area for the air to rub against and cause rug burn.
Yeah.
But it has no bulky shape to create a wake, so it's all friction.
Exactly. But now take that exact same flat plate and turn it vertically. Turn it 90 degrees so it is acting like a wall against the oncoming wind.
Yeah. Oh, now it's a completely different story. It's a sail.
Completely different.
Right.
Now, the wind is slamming directly into the flat, broad face, creating a massive high-pressure zone.
And behind the plate?
Behind the plate, there is a monstrous low-pressure wake.
So it's all pressure drag now.
Right. In this vertical orientation, almost 100% of the drag is pressure drag. The friction drag on those incredibly thin outer edges is essentially zero.
Okay, so the total drag on any object in the world is really just a sliding scale between friction and pressure, and it depends entirely on the object's shape.
That is exactly the takeaway. And this brings us to blunt bodies.
Blunt bodies, like our golf ball.
Right. Things like a circular cylinder or a sphere. A sphere is kind of the worst of both worlds, aerodynamically speaking.
Why is that?
The textbooks show that for a blunt cylinder or a sphere moving through a fluid, pressure drag accounts for roughly 97% of the total drag force.
Wait, 97%?
Yes. Friction drag accounts for only about 3%.
Okay, wait, pause right there. I have to challenge you on that 97% number.
Yeah, go for it.
Because, look, if I am driving down the highway at 60 miles an hour, right, and I roll down the window and stick my hand out holding my palm forward like a blunt object.
The classic road trip move.
Exactly. When I do that, I feel the wind ripping violently across my skin. It feels like surface friction is doing all the work of pushing my hand backward.
It really does feel that way.
Are you seriously telling me that all that intense friction I'm feeling on my skin is just a 3% rounding error?
I know, it is entirely counterintuitive. And it's because human beings can feel the wind rubbing on our skin, but we cannot feel or see the giant, invisible vacuum of low pressure that we are dragging behind us.
We just can't sense the wake.
Right. When you hold your palm forward out that car window, the main reason your arm gets exhausted trying to hold it there isn't because the air is rubbing the sides of your fingers.
It's not.
No, it is because you are creating a high-pressure stagnation point on your palm and a huge, swirling, low-pressure void right behind the back of your hand. That empty void is trying to suck your arm toward the back of the car. That invisible pressure differential is responsible for 97% of the force your muscles are fighting.
That is wild. Our own senses completely lie to us about what is actually slowing us down in the real world.
They absolutely do. And this blind spot is the crux of the golf ball paradox.
How so?
Well, think about it. If you are an engineer and you want a golf ball to fly 300 yards, you really don't care about the 3% friction drag.
Right. Why bother fixing 3%?
Exactly. You have to solve the 97% problem. You have to reduce the pressure drag.
Okay, so you have to shrink the wake.
Yes. And to understand how to do that, you have to ask, what is actually causing that massive low-pressure void behind the sphere in the first place?
I'm asking exactly that. Like, if the air just flowed smoothly around the front of the ball and then perfectly closed back in together on the back of the ball, there wouldn't be a void, right?
Theoretically, yes.
So why doesn't the air just hug the shape of the sphere the whole way around? Why does it leave a wake at all?
To answer that, we have to zoom in incredibly close to the surface of the ball.
How close are we talking?
Microscopic. We have to examine a phenomenon known as the boundary layer. The boundary layer is the literal friction point where the entire disaster of pressure drag is born.
Okay, let's zoom in. What exactly is the boundary layer?
To really appreciate the boundary layer, you have to understand the massive historical crisis in fluid dynamics that happened right before 1904.
A crisis in fluid dynamics. That sounds dramatic.
It was for mathematicians. During the 18th and 19th centuries, these brilliant mathematical minds like Euler and Bernoulli developed incredibly elegant equations for fluid flow.
I've heard of Bernoulli's principle.
Right. But they developed all this math by assuming fluids were ideal, meaning they assumed fluids had absolutely zero viscosity, zero friction.
Wait, so they just pretended friction didn't exist just to make the math easier to solve?
Essentially, yes. And for fluids like air and water, which naturally have very low viscosity compared to something like honey, it actually seemed like a somewhat reasonable assumption at the time.
I guess. But surely that caused problems.
It led to a massive problem. It became known as D'Alembert's paradox.
What was the paradox?
Well, these ideal mathematical models definitively proved that an object moving through a frictionless fluid should experience exactly zero drag.
Zero drag. But any engineer who has ever built a boat or thrown a rock knows that is completely false.
Exactly. The mathematicians were creating these beautiful equations that proved drag didn't exist, while the actual engineers were out there building ships and steam trains and fighting massive amounts of drag every single day.
That is hilarious. There was just this huge disconnect between theoretical math and practical reality.
It's a huge disconnect. And they couldn't figure out how to reconcile it.
So how did they finally bridge that gap?
It was finally solved by a German physicist named Ludwig Prandtl in 1904.
1904.
He presented a paper at the Third Congress of Mathematicians in Heidelberg, and it just revolutionized the entire field of aerodynamics.
What did he figure out?
Prandtl realized that you cannot ignore viscosity, you can't ignore friction, but he also realized you don't have to apply the math of friction to the entire ocean of air.
Okay.
He proposed dividing the flow field into two completely distinct regions. You have the vast free stream out in the open, far away from the object, where you actually can pretend viscosity doesn't exist.
So the math works out there.
Right. And then he defined a second region, an incredibly thin microscopic layer of air immediately adjacent to the surface of the object.
And he called
this the boundary layer.
the boundary layer, okay?
Yeah.
And what makes this microscopic layer of air so incredibly special?
It is the only place in the entire fluid where the most important rule in fluid mechanics is strictly enforced.
Which rule is that?
The no-slip condition.
The no-slip condition, meaning the fluid is forbidden from slipping.
Exactly. When a fluid comes into direct physical contact with a solid surface, molecular interactions cause the fluid molecules to seek thermal and kinetic equilibrium with that solid.
Okay, so they interact on a molecular level.
Right. The fluid doesn't just slide past the surface, it sticks to it completely. The velocity of the fluid exactly at the wall is zero relative to the wall.
Hold on. If that's true, think about a commercial airliner flying at 500 miles an hour.
Okay.
Are you seriously telling me that the microscopic layer of air molecules actually touching the aluminum paint on the nose of that jet is moving at exactly 0 miles an hour relative to the plane?
That is exactly what I'm saying.
That's insane.
The molecules directly touching the paint are dragged perfectly along with the aircraft. They are essentially captive to the plane.
Wow.
But the air, just a tiny, tiny fraction of an inch away from the plane, is rushing past at the full 500 miles an hour.
So that is a staggering gradient of speed in a microscopic amount of space.
It is extreme. You have this incredibly thin boundary layer where the air velocity goes from zero right at the surface and then ramps up violently and rapidly to the full 500-mile-an-hour speed of the free stream, just a millimeter or two away.
And all the friction happens right there in that gap.
Yes. All of the viscous effects, all of the shear stress, all of the intense friction in the entire fluid flow are confined entirely within this one microscopic boundary layer.
So Prandtl basically isolated all the friction to this tiny skin of air wrapped tightly around the object.
He did. And this boundary layer is what dictates absolutely everything that happens to our golf ball.
Why is it so crucial for the golf ball?
Because as the air flows over a blunt object like a sphere, that thin, exhausted layer of captive air has to negotiate rapidly changing pressures across the surface.
Okay, let's track that. Let's trace a single particle of air as it hits the dead front of the golf ball and tries to make its way over the top and around to the back.
Okay, let's do it. So on the very front half of the sphere, the geometry of the ball is curving away from the center line, right?
Right, it's rounding outward.
As the air moves from the very front, what we call the stagnation point, and flows up towards the equator or the top of the sphere, the area for the flow is actually getting narrower.
Because it's squeezing over the top.
Exactly, which forces the air to accelerate. And according to Bernoulli's principle, when fluid accelerates, its pressure drops.
Okay, so the pressure is highest at the dead front where it crashes into the ball, and the pressure gets lower and lower as you go over the top curve.
Yes. This is called a favorable pressure gradient.
Favorable. So the air likes this.
The air in the boundary layer loves this. It is moving from a zone of high pressure to a zone of lower pressure. The decreasing pressure is essentially pushing it from behind, helping pull it along the surface.
I picture that kind of like coasting downhill on a bicycle. You don't even have to pedal. The gradient is just doing all the work for you.
That's a great analogy. But once our air particle reaches the top of the sphere, the equator, and starts trying to curve around the back half of the ball, the geometry changes again.
Because now the ball is curving inward.
Right. Now, the shape of the sphere is expanding away from the flow. The flow area is getting wider, which means the air velocity starts to decrease.
And as velocity decreases,
the pressure rises.
So now the air is moving from a lower pressure zone at the top into a higher pressure zone at the rear of the ball.
Yes. And this is known in fluid dynamics as an adverse pressure gradient.
Adverse, as in hostile.
Highly hostile to the boundary layer.
Why is it so hostile?
Well, think about the fluid in that incredibly thin layer right near the surface. It has already lost a tremendous amount of its kinetic energy because of the intense friction, right?
Oh, right. Because it's constantly being dragged to a halt by the no-slip condition at the wall.
Exactly. It is exhausted. And now, suddenly, after losing all that energy, it has to push forward against an invisible wall of increasing pressure on the back of the ball.
I'm trying to picture a physical analogy for this. It feels like, okay, imagine you are driving a car on the highway, and you're coasting downhill, building up tons of speed.
Right, that's the favorable gradient on the front of the ball.
Yeah, but at the very bottom of the hill, you run completely out of gas.
A total loss of internal energy, very similar to the friction loss in the boundary layer.
Right, and immediately after you run out of gas, the road pitches upward into a massive, steep hill, and suddenly there is a hurricane-force headwind blowing against the front of your car.
That headwind is your adverse pressure gradient.
Right, so you have no engine power left, you're fighting gravity going uphill, and you're fighting a massive headwind. Your forward momentum is going to bleed off incredibly fast.
Yes, it is.
Eventually, the car is just going to slow to a complete stop on the hill, and then probably start rolling backward.
That is a brilliant way to conceptualize it, because that is exactly what happens to the fluid deep down in the boundary layer. It loses all its forward momentum fighting the adverse gradient.
It just stops.
The velocity of the fluid near the wall drops to absolute zero, and the flow physically cannot push forward against the high pressure anymore. And at that exact point, the fluid completely breaks away from the surface of the object.
It detaches.
It detaches. This phenomenon is called flow separation. The boundary layer literally peels off the body of the sphere and shoots straight out into the free stream.
Flow separation. The air just completely gives up trying to hug the shape of the ball.
It gives up. And what happens in the space where the air gave up?
A void.
Exactly.
Okay.
It leaves behind a massive, swirling, chaotic void. This early separation creates a broad, pulsating, low-pressure wake directly behind the object. The main flow of air is completely deflected around this giant turbulent dead zone.
And this brings us all the way back to the 97% problem from earlier.
It does.
This massive low-pressure wake is what causes all the pressure drag. This is the giant vacuum that is sucking the golf ball backward out of the sky.
Precisely. For any blunt body, the exact physical location where that boundary layer finally separates determines the overall size of the wake.
Oh, I see.
Right? If it separates really early, say, right at the top of the sphere, you get a gargantuan wake and a catastrophic pressure drag.
But if you can delay it.
If you can coax the boundary layer to hold on and separate much later, further down the back of the ball, the resulting wake is much narrower and the pressure drag is significantly lower.
So if you are an engineer designing a golf ball today, your entire existence is focused on one single goal. You need that boundary layer to hang on for dear life.
Yes.
You need to delay flow separation for as long as physically possible.
That is the holy grail of aerodynamics for blunt bodies, delaying separation.
But how? I mean, if the air is totally exhausted by the no-slip condition and it hits that hurricane headwind of the adverse pressure gradient, how can we possibly stop it from giving up?
It seems impossible, right?
It does. Can we, like, inject a burst of energy into that exhausted layer of air to help it push further up the hill?
Actually, we can.
Wait, really? How?
But to do it, we have to fundamentally alter the structural nature of the boundary layer itself. We have to talk about the two distinct regimes of fluid flow.
Oh, okay. I am intrigued. How do we change the flow itself?
To understand this, we need to introduce the single most important dimensionless parameter in all of fluid mechanics. It's called the Reynolds number.
The Reynolds number. I feel like anyone who has ever watched a documentary on airplanes or submarines has heard this term thrown around. But what is it, actually? What does it measure?
It was popularized by an Irish engineer named Osborne Reynolds in the late 19th century.
Okay.
The Reynolds number is simply a mathematical ratio. The equation is the density of the fluid multiplied by the velocity of the fluid multiplied by a characteristic length of the object, all divided by the dynamic viscosity of the fluid.
Okay, that is a lot of variables. Let's ground that a bit.
Right.
Density, velocity, length, divided by viscosity.
I know, it's a mouthful. In plain terms, the Reynolds number simply represents the ratio of inertia forces to viscous forces in a fluid flow.
Inertia versus viscosity. Break that down for me.
Inertia forces are the forces related to the fluid's mass and its speed. It is the fluid's momentum, its aggressive tendency to just keep moving forward in a straight line.
Okay, momentum pushing forward.
Viscous forces, on the other hand, are the forces of internal friction and stickiness within the fluid that are trying to bind it together and slow it down.
Okay, so a low Reynolds number means the denominator, the viscosity, the stickiness is dominating the equation.
Exactly.
So the flow is thick, sticky, and slow. Kind of like pouring cold honey off a spoon.
That is exactly it. And a high Reynolds number means the numerator, the inertia, the speed, and the mass is dominating.
So the flow is fast, forceful, and the internal stickiness matters much less, like a jet stream or water blasting out of a fire hose.
Precisely. So the Reynolds number just tells us who is winning the fight in the fluid, momentum or stickiness.
And whoever is winning dictates which of the two flow regimes you are in.
Yes. The fluid will exist in either laminar flow or turbulent flow.
Laminar and turbulent. Okay, let's start with laminar flow. What is that?
This regime occurs at lower Reynolds numbers, where viscosity has a really strong influence. Laminar flow is smooth, orderly, and highly predictable.
Smooth and orderly.
The fluid flows in perfect parallel layers, or laminas, with absolutely no macroscopic mixing or disruption between the layers.
I picture that like perfectly stacked sheets of paper sliding over each other.
Yes, very much like that.
Or, you know when you turn a bathroom faucet on just a tiny bit and the water comes out in a perfectly clear, glassy, unbroken stream?
That glassy stream is the perfect example of laminar flow. Osborne Reynolds actually demonstrated this in a really famous 1883 experiment.
What did he do?
He injected an incredibly thin, continuous streak of colored dye into water that was flowing through a clear glass tube. At low speeds, meaning low Reynolds numbers, the dye streak remained a beautifully straight, unbroken, distinct line all the way down the tube.
Ah.
The layers of water were sliding past each other so perfectly that the dye literally never mixed with the surrounding water.
It sounds incredibly elegant and mathematically perfect.
It is mathematically elegant, but in the real brutal world of aerodynamics, that order has a fatal weakness.
What's the weakness?
While laminar flow is beautiful, a laminar boundary layer is highly vulnerable to adverse pressure gradients.
Why? If it's so smooth and frictionless, shouldn't it just slip right through the gradient?
You'd think so, but no, because the layers don't mix.
Okay.
Think back to our boundary layer. The fluid layer right next to the wall, the one stuck by the no-slip condition, is fighting a brutal battle against friction. It is actively bleeding kinetic energy.
Right.
Now, just a fraction of a millimeter above it, in the exact next layer, the fluid is moving much faster. But because it is a laminar flow, there is no crosstalk between the layers.
Oh, I see.
The fast layer doesn't share any of its energy with the slow dying layer right next to the wall.
Ah, so the layer on the wall is totally isolated. It is fighting the uphill battle of the adverse pressure gradient all by itself, while the rich, fast-moving air right above it just coasts on by without helping at all.
Precisely. Because it gets absolutely no kinetic help from the outer flow, the laminar boundary layer exhausts its momentum very quickly when it hits the adverse pressure gradient on the back of a sphere.
It just dies.
It dies. It separates incredibly early.
So a laminar boundary layer is essentially useless for keeping drag low on a blunt object.
It is the absolute worst-case scenario. Now let's contrast this with turbulent flow.
Okay, the opposite.
As you increase the velocity of the fluid or you increase the size of the object, the Reynolds number goes up. At a certain critical threshold, those smooth, sliding layers become unstable and completely break down. The flow transitions to turbulent.
What's the threshold?
For flow inside a pipe, Reynolds found this transition happens around a Reynolds number of 2300. For air flowing over a flat plate, it's much higher, around a Reynolds number of 500,000.
Okay, and what happens to our clear, glassy stream of water from the faucet when it goes turbulent?
It becomes chaotic, it becomes random and rapidly fluctuating.
Like when you blast the faucet on full volume.
Exactly. If you inject that same streak of dye into a turbulent flow, it doesn't form a straight line. It immediately disperses, churning and mixing violently in every single direction. The velocity of the fluid at any given microscopic point is constantly vibrating and fluctuating wildly around a mean value.
So it's a complete mess.
It is a complete mess, but, and this is crucial in aerodynamics, that messiness is a superpower.
Really? Why?
Because of all that chaotic churning, all those microscopic vortices and the aggressive mixing, momentum is constantly being transferred vertically between the different layers of the fluid.
They're sharing energy.
Exactly. The fluid dynamics texts describe the complex structure of a turbulent boundary layer as having three distinct zones. You have a viscous wall layer, an overlap layer, and a turbulent outer layer.
And how do those zones interact with each other?
They act like a violent conveyor belt. The swirling eddies in the turbulent flow are constantly taking high-speed, high-momentum fluid from the outer edges of the boundary layer and aggressively whipping it down closer to the wall.
Okay, I'm going to use an analogy here to make sure I really grasp this difference.
Please do.
Think of laminar flow, like a polite, orderly line of people waiting for a bus.
Okay, polite line.
Everyone stays in their designated spot. They move forward slowly. It's very organized.
Yeah.
But if a bully representing the adverse pressure gradient comes up and shoves the person at the very front of the line, that person just falls over.
Right.
The line breaks apart easily because no one is holding on to each other or helping the person in front.
It's a fragile order. The person in front is completely isolated.
Exactly. But turbulent flow is not a line. Turbulent flow is a high-energy mosh pit at a heavy metal concert.
Oh, I like this.
It is completely chaotic. People are vibrating, sweating, flying in every direction. It looks like a total disaster from the outside. But because everyone is constantly colliding, interlocking arms, bouncing off each other, and transferring energy, the mosh pit as a whole entity has incredible unified momentum.
It does.
If that same bully tries to shove the edge of a mosh pit, the mosh pit pushes back. It absorbs the blow and holds its ground against outside forces because it is constantly sharing kinetic energy throughout the entire group.
That is a phenomenal conceptualization. The turbulent boundary layer is exactly that. A microscopic, high-velocity marsh pit.
A microscopic mosh pit.
Because it is constantly churning high-speed air down from the top layers to the surface, the fluid immediately adjacent to the wall is continually re-energized. It has dramatically more kinetic energy than it would in a weak laminar state.
And because it has more energy.
It is far, far more resistant to an adverse pressure gradient. When that energized, churning, turbulent boundary layer hits the hurricane headwind on the back of a sphere, it doesn't just run out of gas and give up immediately.
It fights back.
It fights its way much, much further around the rear curve of the object before it finally succumbs and separates.
It aggressively clings to the surface.
It clings to the surface. And this fundamental lesson in fluid mechanics, the fragile isolation of laminar flow versus the energetic clinging of turbulent flow, this is the master key that finally unlocks the core mission of our deep dive today.
Yes. Let's finally bring all of this theoretical physics back to the golf ball.
Let's do it.
We have all the pieces on the board now. We know that pressure drag from the giant wake is the ultimate enemy.
Yes.
We know that flow separation is what creates that wake. And we now know that a chaotic, turbulent boundary layer resists separation infinitely better than a smooth laminar one.
Exactly.
So what is actually happening when Tiger Woods hits a perfectly smooth sphere versus a dimpled golf ball?
Let's look at the actual mathematical reality of a golf shot. When a professional hits a drive, the golf ball typically flies through the air at a velocity and a length scale that yields a Reynolds number of about 10 to the fifth power.
10 to the fifth power, so roughly 100,000.
Right, a Reynolds number of roughly 100,000. Now, if a golf ball were perfectly smooth and polished, at that specific Reynolds number of 100,000, the boundary layer forming on its surface would naturally remain in the laminar regime.
It wouldn't turn turbulent on its own.
No. The inertia forces aren't quite high enough yet to naturally break it down into turbulence.
So the smooth ball generates the polite, fragile line of people waiting for the bus.
Exactly. And we know exactly how a laminar boundary layer behaves on a sphere. It accelerates over the front, hits the equator, and immediately slams into the adverse pressure gradient.
And because it has no internal mixing to help it.
It fails catastrophically. The fluid dynamics data shows that for a smooth sphere at this speed, laminar flow separates very early at an angle of approximately 80 degrees from the front stagnation point.
Wait, 80 degrees?
80 degrees.
90 degrees would be the dead center equator of the ball. You're saying the air gives up and detaches before it even reaches the halfway point.
Yes. It separates before it even gets to the middle of the ball.
That is disastrous.
It really is. This premature separation creates a massive, gaping, cavernous, low-pressure wake directly behind the ball.
It must be huge.
The wake is almost as wide as the ball itself, and because of this massive void, the pressure drag is enormous. The drag coefficient, which is the dimensionless number engineers use to quantify total drag resistance, it sits at a hefty 0.5.
So a smooth golf ball punches this huge, ugly, turbulent hole in the air, creating a giant vacuum that just sucks it backward and kills all its forward
It
momentum.
would lose its speed almost immediately and plummet to the fairway. Now enter the genius of the dimples.
And dimples,
Yeah.
the 300 or so little craters covering the surface, what are they actually doing physically to the air?
The dimples act as deliberate, highly engineered surface roughness. They are intentionally designed geometric imperfections.
Okay.
As that thin layer of air flows over these hundreds of tiny craters, the sharp edges of the dimples literally trip the boundary layer. They act like microscopic speed bumps that force the smooth laminar flow to become unstable and chaotic much earlier than it naturally would.
They intentionally start the mosh pit.
They forcefully initiate the mosh pit. The dimples trigger an artificial early transition from a weak laminar boundary layer into a highly energetic, turbulent boundary layer.
Wow. And because it transitions to a turbulent mosh pit early, it suddenly has all that extra momentum mixing down to the surface.
Precisely. And because it has that extra momentum, it radically changes how the air negotiates the back of the ball. The turbulent boundary layer clings to the ball's surface.
It goes on.
It fights the adverse pressure gradient much, much more effectively. The separation point is pushed significantly further back. Instead of giving up at 80 degrees, the dimple-induced turbulent boundary layer delays separation until about 120 degrees around the back curve of the ball.
120 degrees. That is a massive geometric difference. The air is hugging the ball way past the equator, curving deep around the rear.
It changes the entire aerodynamic profile. By delaying the separation from 80 degrees all the way back to 120 degrees, the overall size of the resulting wake is dramatically narrowed.
It shrinks the void.
Instead of a gaping void the size of the ball, you have a much smaller, tighter, narrower wake trailing behind it.
And a smaller wake means a smaller vacuum.
A smaller wake means a massive, game-changing reduction in pressure drag. The pressure imbalance between the front and the back is drastically reduced.
Incredible.
Now, to be scientifically rigorous, we must acknowledge that making the surface rough and triggering all that chaotic turbulence does actually increase the friction drag slightly.
Oh, sure, that makes sense.
Yeah.
A turbulent mosh pit rubbing against a rough, dimpled surface is obviously going to generate more shear stress than a smooth sheet of air gliding over polished plastic.
Yes. The skin friction absolutely goes up. But remember our shape factor discussion from earlier?
Right, the 97% rule.
Exactly. For a blunt sphere, friction drag only accounts for about 3% of the total problem. Pressure drag is 97% of the problem.
Wow.
So the massive reduction in pressure drag gained by narrowing the weight overwhelmingly almost laughably compensates for the tiny penalty of increased skin friction.
It is the ultimate aerodynamic trade-off. You knowingly sacrifice a tiny bit of friction to completely slay the monster of pressure drag.
It is brilliant engineering. Let's look at the final astonishing numbers from the textbooks.
Let's hear them.
By inducing that turbulence with dimples, the total drag coefficient of the golf ball plummets from 0.5 down to 0.2.
Wow. From 0.5 to 0.2.
That is a staggering 60% reduction in total aerodynamic drag.
60%.
Just by making the surface rough and bumpy. This 60% reduction is literally the only reason a golf ball can maintain its velocity and travel 300 yards down the fairway.
If you're listening to this and trying to wrap your head around it, just think about what this actually means.
It's wild.
It means that making an object rougher, bumpier, and more chaotic on its surface actually makes it slice through the air significantly better.
Yes.
This is such a profound, counterintuitive physics hack. We spend all our time polishing cars and waxing airplane wings, but for a blunt object flying at this specific Reynolds number, perfect smoothness is literally the worst possible design. You have to manufacture chaos to achieve efficiency.
Manufactured chaos is a perfect description. The dimples are manipulating the invisible physics of the boundary layer to extract maximum performance.
So cool.
But, and here is where the story gets even more complex, drag reduction is actually only half the story of a golf ball's incredible flight.
I'm with you. Because a golf ball doesn't just cut through the air like a bullet, right? It hangs in the air.
It floats.
When you watch a professional hit a drive, the ball starts low and then literally seems to rise and float upward, defying gravity for several seconds.
It does.
How is a round, blunt object generating upward lift? It doesn't have wings.
That phenomenon brings us to our next major concept from the fluid dynamics literature, something known as the Magnus effect.
The Magnus effect.
Oh.
If I recall correctly, this has everything to do with spin.
It does. When a golf club strikes the ball, the club face is angled, it has loft.
Right.
So the club doesn't just hit the ball dead center and push it forward perfectly straight. The lofted face slides down the back of the ball during impact, imparting a massive amount of backspin.
How much spin are we talking?
A driver can put 2,000 to 3,000 revolutions per minute of backspin on the ball. A wedge can put 10,000 RPMs on it.
10,000. So the ball is hurtling forward through the air at 150 miles an hour while simultaneously spinning violently backward on its horizontal axis.
Exactly. Now, we have to bring back our golden rule of fluid dynamics from earlier, the no-slip condition.
Oh, right. The air stuck to the ball.
The fluid directly touching the surface of the ball must move at the exact same speed and direction as the surface itself. Because the ball is spinning so violently, the rough, dimpled surface is physically dragging the boundary layer of air around and around in a circle with it.
Okay, I am visualizing this, and it feels like a major collision of forces.
It is.
The ball is moving forward, which means a hurricane of free stream air is rushing past it from front to back. But the ball is also spinning backward, dragging a layer of air in a circle. How do those two airflows interact?
They interact by creating a massive asymmetry. Let's isolate the top and the bottom of the spinning ball for a second.
Okay, looking at the top.
On the top of the ball, the surface is spinning backward towards the rear of the ball. This is the exact same direction that the oncoming free stream air is trying to flow over the top.
Oh.
So the violent rotation of the ball is literally helping to pull and accelerate the air over the top surface. The air moves much, much faster over the top.
I see that. It's like walking on a moving walkway at the airport. Your walking speed is just added to the belt speed.
That is a perfect analogy. But on the bottom of the ball, the exact opposite is happening.
The walkway is moving against you.
Exactly. The surface of the ball is spinning forward, directly into the face of the oncoming free stream air. The rotation of the ball is physically fighting the rushing air. creating this massive traffic jam that severely slows down the airflow across the bottom surface.
So the air on the top is supercharged and speeding up, and the air on the bottom is fighting a headwind and slowing down.
Yes. The spin creates a profound asymmetry in the velocity of the flow field around the ball. And wherever you have a difference in fluid velocity, Bernoulli's principle dictates that you will have an inverse difference in fluid pressure.
Right. Fast means low pressure, slow means high pressure.
Fast-moving air exerts lower pressure. Slow-moving air exerts higher pressure.
Hold on, if that's true.
Yeah.
The air on top is moving faster, so it creates a zone of low pressure on the top of the ball.
Yes.
And the air on the bottom is moving slower, so it creates a zone of high pressure on the bottom of the ball.
That is entirely correct.
High pressure pushing up on the bottom, low pressure vacuum pulling up on top.
Yeah.
That means the spinning ball is literally being pushed upward into the sky.
Exactly. That massive pressure difference creates a net upward force that fights gravity. The side force generated by a spinning object in a moving fluid is called the Magnus effect.
The Magnus effect.
Named after the German physicist Heinrich Magnus, who formally described it mathematically way back in 1852.
This is blowing my mind because this explains so much more than just golf.
Oh, absolutely.
This is the exact same reason a baseball pitcher can throw a curveball, right?
Yes.
Or how a soccer player can bend a free kick around a wall of defenders into the top corner of the net.
It is the exact same physics. If you strike a soccer ball on the side, imparting a sideways spin on a vertical axis, the high and low pressure zones form on the left and right sides of the ball. The Magnus effect pushes the ball sideways, causing it to curve dramatically in midair.
Wow.
With a golf ball, the backspin aligns the high pressure on the bottom and the low pressure on top, so the ball curves upward, fighting gravity and generating tremendous lift.
Manipulating the fluid boundary layer with spin is literally the secret invisible weapon in almost every single sport involving a ball.
It truly is, and our sources provide a much deeper mathematical foundation for why this lift occurs, known as the Kuta-Joukowski lift theorem.
Kuta-Joukowski?
Oh.
Okay, that sounds incredibly dense.
It is a cornerstone of theoretical aerodynamics, developed independently by Martin Kuta in Germany and Nikolai Joukowski in Russia in the early 1900s.
What does the theorem actually say?
The theorem relates the lift generated by any object, whether it's a spinning cylinder, a golf ball, or the wing of a Boeing 747, to a mathematical concept called circulation.
Circulation. What does that mean mathematically? I assume it doesn't mean blood flow.
No, in fluid dynamics, circulation is a mathematical line integral that measures the macroscopic spin or rotation of the entire fluid field around a body.
How do you measure that?
Imagine drawing a large imaginary circle in the air, completely surrounding our golf ball. If you measure the velocity of the air tracing along that circle, and you find that the air is collectively rotating in one direction more than the other, you have circulation.
And the spinning golf ball creates that circulation because it's dragging the boundary layer, which in turn drags the air around it.
Exactly. The Kuta-Joukowski theorem mathematically proves that if you have a free stream of air moving at a certain velocity, and you impose a circulation on the object within that stream, you will inherently generate a lift force perpendicular to the flow.
So it's guaranteed lift.
The lift is directly proportional to the density of the air, the velocity of the air, and the amount of circulation.
So the math finally proved what every golfer and baseball player already knew instinctively. Spin equals movement.
Yes. And what is fascinating is that engineers didn't just leave this theory on the sports field. They tried to harness the Magnus effect to power massive industrial machines.
Wait, really?
The textbook highlights one of the most incredible historical examples of applied fluid dynamics: the Flettner rotor ship.
Oh, I saw this mentioned in the notes. A ship powered by giant spinning pillars.
Yes. In 1924, a visionary German engineer named Anton Flettner designed and built a ship called the Buckow. But he didn't use canvas sails or massive steam engines.
What did he use?
Instead, he erected two massive vertical steel cylinders on the deck, each 50 feet tall and 9 feet wide.
50 feet tall.
And he installed small electric motors inside to spin these massive cylinders at really high speeds.
Wait, so it's just a boat with two 50-foot spinning silos on the deck. How on earth does that propel a heavy steel ship through the ocean?
By using the exact same physics as a bending soccer kick.
Magnus effect.
Exactly. When the wind blew across the ocean and hit those 50-foot spinning cylinders, the no-slip condition dragged the boundary layer. The Flettner rotors created massive circulation in the wind flow.
And that created a side force.
The Magnus effect generated a gargantuan side force perpendicular to the wind direction. Flettner simply calculated the angles and harnessed that massive side force as forward thrust to propel the ship.
That is insane. Did it actually work in the real world?
It worked flawlessly. The Buckow successfully and efficiently crossed the Atlantic Ocean.
No way.
Yes. The measured lift-to-drag ratio from these rotating cylinders is actually dramatically larger than you can achieve with a traditional canvas sail of the exact same size.
So why don't we see them everywhere today?
Ultimately, Flettner ships didn't take over the world commercially back then, largely because cheap diesel engines were becoming incredibly reliable and required fewer moving parts.
Right, diesel is just easier.
But it proved the physics of the Magnus effect on a massive industrial scale.
That is incredible to think about. From the microscopic dimples on a tiny golf ball to 50-foot spinning steel pillars dragging a whole ship across the Atlantic, the fundamental laws of fluid dynamics just scale perfectly.
They do scale perfectly. And that scalability brings us to a really crucial question for modern engineering.
Which is?
We know how boundary layers, turbulence, and circulation work in theory, but how do we actually design complex shapes using these principles today? We can't just build full-size Flettner ships and see if they sink, or carve 10,000 slightly different golf balls by hand to find the mathematically perfect dimple pattern.
Right, physical prototyping is incredibly expensive and painfully slow. So if you're an engineer at Callaway or Titleist trying to invent the next generation of golf ball, or an aerospace engineer designing a new wing, how do you manipulate these invisible forces without spending years in a wind tunnel?
This is where we pivot from the physical world into the digital world, and we dive into our final set of sources for this deep dive, the highly technical manuals from ANSYS Fluent.
Okay, the software manuals.
Today, the world of aerodynamics is entirely dependent on CFD, or computational fluid dynamics.
CFD. I've heard this acronym used a lot in Formula One racing and aerospace. It's essentially a virtual computerized wind tunnel, right?
That is a highly accurate way to think about it. CFD uses supercomputers and incredibly complex software to numerically solve the Navier-Stokes equations.
The Navier-Stokes equations. Those are famous for being nearly impossible to solve, right?
They are notoriously difficult. They are a set of differential equations that describe how the velocity, pressure, temperature, and density of a moving fluid relate to one another.
And we can't solve them.
They are so complex that there is no known analytical, exact mathematical solution for them in three-dimensional space. In fact, it is one of the Millennium Prize problems in mathematics.
Wait, so if humans haven't solved the underlying math, how does the computer software simulate the fluid?
Because computers can't solve these equations continuously for every single infinite point in a volume of space, the software uses a technique called discretization.
Discretization, meaning to chop something continuous up into tiny discrete pieces.
Exactly. Engineers create a mathematical mesh around a 3D digital model of their object.
A mesh, like a grid.
Imagine you have a digital 3D model of a new car design. The software essentially wraps the entire car and a large volume of the air around it in a 3D grid made of millions of tiny little geometric pyramids, tetrahedrons, or hexahedrons.
Little blocks.
These tiny individual blocks are called cells.
Okay, so you build a digital world made of microscopic Lego blocks, and instead of trying to solve the wind for the whole world at once, the computer just calculates the physics inside every single tiny block.
Right. The supercomputer calculates the pressure, velocity, and turbulence of the air as it moves from one single microscopic cell into the cell right next to it, one incredibly small fraction of a second at a time.
It just grinds through it.
It brute forces the math across millions of data points to build a macro simulation of the flow.
That makes sense. But how does this relate to the golf ball paradox we've been talking about?
Here is where the ANSYS Fluent manual gets incredibly specific, and it ties directly back to everything we just learned about Prandtl and the boundary layer.
Oh, the no-slip condition layer.
Remember how incredibly thin the boundary layer is?
Yes, it's that microscopic film of captive air right on the skin of the object where the no-flip condition applies, and where all the friction and flow separation actually happens.
Because that layer is so infinitesimally thin, but so absolutely critical because it completely dictates the separation point and the massive pressure drag, you cannot use standard-sized geometric cells in your mesh near the surface of the object.
Why not?
If you make your digital mesh cells larger than the physical thickness of the boundary layer, the computer won't even see the boundary layer.
Oh, I see the problem. If your digital block is an inch tall, but the real boundary layer is only a millimeter thick, The computer just averages out the math for that whole inch, completely missing the violent friction and zero velocity gradient happening at the wall.
Exactly. It would just average it out. The simulation would fail to predict flow separation entirely, and it would output a completely incorrect, artificially low drag number.
Your data would be garbage.
Your digital simulation would be absolutely worthless. So CFD engineers have to perform a highly specialized, obsessive process called meshing the boundary layer.
How do they do that? Do they just make all the blocks everywhere microscopic?
They can't. If they made all the cells microscopic everywhere, there would be trillions of them, and the simulation would take centuries to compute.
Right, supercomputers have limits.
Instead, they create specialized structures near the wall that the ANSYS manual calls inflation layers.
Inflation layers, what do those look like?
Instead of standard 3D pyramids, inflation layers are extremely fine, flattened, geometrically precise layers of rectangular cells that are drawn directly next to the physical wall of the 3D model.
Flattened cells.
They conform perfectly to the curves of the object. Imagine incredibly thin, tightly packed layers of an onion wrapping the skin of the car or the golf ball.
So you are basically hand-drawing a high-resolution mathematical boundary layer onto the digital model, right where you know the chaos is going to happen.
Yes, and the manual details very strict, unforgiving parameters for how these layers must be built. The single most critical parameter is a value called the first height.
First height. I'm assuming that means the physical height of the very first cell touching the object.
Precisely. The first height dictates the thickness of that very first row of microscopic digital cells touching the wall.
How thin does it have to be?
The engineer has to calculate exactly how thick the viscous sublayer of the fluid will be at their specific speed and ensure the first height is strictly smaller than that thickness.
And if they don't?
If an engineer gets the first height wrong, if that first digital cell is even a fraction of a millimeter too thick, the software won't accurately capture the shear stress at the wall. It won't capture the violent velocity gradient.
And if it misses that, it misses the exact point where the air gives up and separates.
And if you miss the separation point, you miss the size of the wake, and your prediction of pressure drag is completely wrong.
Okay, this is where the scale of what we were talking about just melts my brain.
It is pretty staggering.
You have aerospace engineers building massive digital wind tunnels to simulate a commercial passenger jet that is hundreds of feet long and weighs hundreds of tons, right?
Yeah.
But to make that massive simulation actually work and give them real data, they have to obsess over a microscopic layer of mathematical cells right on the aluminum skin of the airplane, defining the first height down to the micrometer just to see if the air will properly get exhausted and separate in the software.
It is a phenomenal, almost poetic contrast in scale.
Poetic is a good word for it.
The macro, real-world performance of a massive jetliner or the flight path of a golf ball is entirely mathematically dependent on the microscopic precision of that first inflation layer in the digital CFD mesh. It all comes down to the smallest detail.
Are there other parameters for these layers?
Yes. The ANSYS manual also heavily emphasizes another parameter called the growth rate.
What is the growth rate?
Well, once you establish that microscopic first height, you can't just jump immediately back to giant cells in the next layer.
Oh, because the math would jump too fast.
The math would break. So the growth rate dictates how each successive layer of cells moving away from the wall grows slightly larger. Usually it's increased by a factor of 1.2.
So the layers slowly expand and fan out?
Exactly. You start microscopic at the wall where the physics are most intense, and you slowly, mathematically expand the cells as you get further away from the skin, transitioning smoothly out into the free stream where the air is calm, and you can use larger, less computationally demanding blocks.
It sounds incredibly tedious to build.
It is incredibly tedious. They have dedicated software tools specifically for identifying deviated faces to ensure that this complex wrapping of cells perfectly matches the original CAD geometry.
Why is that so important?
Because if the mesh has even a slight accidental digital wrinkle in it, that digital wrinkle will act like a physical dimple. It will artificially trip the boundary layer in the simulation and completely ruin the data. Building a perfect CFD mesh is an art form as much as it is a science.
It really is. It's like painting with mathematics to capture something that is completely invisible to the naked eye.
That's a beautiful way to put it.
And that profound invisible reality brings us full circle on this deep dive. Let's summarize the incredible journey we've taken today.
We covered an immense amount of ground, from theory to simulation.
We really did. We started by redefining how we see the world, recognizing air as a yielding fluid. We broke down the basic struggle between friction and pressure drag, realizing that for blunt objects like a golf ball, the giant low-pressure wake of pressure drag is the ultimate enemy, causing 97% of the resistance.
And we zoomed in to examine Prandtl's boundary layer, understanding the no-slip condition, and watching how that thin film of exhausted air faces the crisis of the adverse pressure gradient, ultimately giving up and causing flow separation.
We contrasted the elegant but fragile isolation of laminar flow with the chaotic, highly energetic, momentum-sharing power of a turbulent mosh pit.
Which perfectly explained the genius of the golf ball. The dimples are an intentional hack. They are engineered surface roughness designed to actively trigger that turbulent mosh pit.
And because that turbulent layer clings to the ball, it delays flow separation, drastically narrows the wake, and plummets the pressure drag by 60%.
An incredible reduction.
Without dimples, the ball is useless. With them, it flies. We also looked at how spin interacts with the boundary layer to create the Magnus effect and Kutaczykowski circulation, generating lift that fights gravity, whether on a tiny golf ball or a massive 1920s Flettner rotor ship.
And finally, we looked at how modern engineers simulate all of this chaotic physics using computational fluid dynamics, obsessing over the micrometer scale first height of their digital inflation layers to accurately capture the invisible forces that dictate our physical world.
It is a true testament to human ingenuity. If you are listening to this, I really hope it fundamentally changes how you look at the world around you.
I hope so too.
The next time you feel the wind roaring past your face, or you watch a curving free kick in a soccer match, or you see an airliner lift off the runway, you shouldn't just see empty space. You are witnessing a complex, incredibly beautiful high-speed physical negotiation between a solid object and the microscopic boundary layer of fluid wrapped tightly around it.
That is the ultimate takeaway. The world is not empty space. It is a fluid puzzle constantly waiting to be solved.
And I want to leave you, the listener, with a final provocative thought to mull over. If you've been listening to this and wondering, well, if dimples work so well for a golf ball, why don't we put dimples on the nose of an airplane or on the hood of a Ferrari? You are hitting on the exact problem engineers face with the Reynolds number.
Exactly. Dimples are optimized for a very specific size and a very specific speed.
Right. The dimples that work perfectly at 150 miles an hour might cause terrible drag at 500 miles an hour.
Surface roughness has to be tuned perfectly to the flow conditions.
But what if the aerodynamic surfaces of the future aren't static? What if they aren't carved in stone? Imagine a high-performance sports car, or a next-generation airplane wing, or even specialized athletic clothing for Olympic sprinters that dynamically alters its own surface texture in real time.
Like a living skin.
Exactly. Imagine a surface made of advanced, shape-shifting metamaterials that can actively grow and retract microscopic dimples on command.
Oh.
A computer could constantly analyze the vehicle's speed, the air pressure, and the Reynolds number, and the skin of the car would ripple and shift, maintaining the absolute perfect, turbulent boundary layer no matter how fast it's moving or how the wind changes.
A fully reactive, programmable aerodynamic surface.
The ultimate aerodynamic vehicle of the future might not look sleek and smooth like glass at all. It might be something that breathes, shifts, and bristles, actively manufacturing the exact amount of chaos needed to slip perfectly through the invisible ocean around us. We might have to redefine our entire aesthetic of what fast actually looks like.
That is a staggering concept to think about. It would revolutionize transportation entirely.
Because as we've learned from the humble golf ball today, sometimes the only way to beat the resistance in front of you is to embrace a little bit of turbulence. Thanks for taking this deep dive with us. Keep questioning the obvious, and we'll see you next time.